Ladies and gentlemen, I'm glad to open the second session on this conference. Let me first introduce myself. My name is Jozef Ritonja. I'm from University of Maribor, from Faculty of Electrical Engineering and Computer Science. The title of this session is Electrical Engineering. This is session 5A, and we have 90 minutes time. 90 minutes for 4 presentations. So there is no problem with time, so if, all of you have more than 20 minutes. So I will start with the first presentation. I'm asking Professor Dobrucky, yes. He will talk about the converters in electric hybrid vehicles. Please.
So, thank you, Chairman, for the introduction. Me and my colleagues here are interested mainly on power electronic systems, and from there, converters, application, and control of the power electronic systems. One of application is hybrid electric drives, of course. So, my title of my presentation is Improving Efficiency of Hybrid Electric Drives. Why? Because efficiency is important parameter of hybrid. Yes, important. So we would like to make it improve this efficiency. The contents of my presentation is, as usual, introduction, direct AC/AC powertrain with efficiency contribution, modeling and simulation, and comparison and conclusion. So the basic idea of our paper is that we would like to substitute this classical serial scheme of hybrid with voltage inverters and traction rectifiers and classical three-phase traction motors by another one using matrix converter. So this is classical, and our scheme we would like to use is like this, but it's not final scheme, it's just idea. Instead of voltage inverters are used matrix converter 3x5, that means 3-phase input, 5-phase output on this. The potential possibilities of efficiency improving of AC/AC powertrain are, it's written here in 6 points, I think. So at first we would like to release the traction rectifier and substitute of classical powertrain by direct AC/AC converter, matrix or cycle converter types. Then we would like to change the classical inverse connected IGBT in series connection by two anti-parallel connected block-in reverse block-in IGBT. It's another possibility is to substitute classical three-phase traction motor by 5-phase motors. Another possibility is use independent control of two traction motors by one single-phase AC/AC converter, matrix converter. And the last possibility is software configuration of direct AC/AC converter for all operation mode of the powertrain, hybrid vehicle powertrain. So this is a better scheme of the using matrix converter, but anyway it's necessary to use this 4-quadrant converter for charging of batteries. So therefore we would like to substitute this converter by connection of matrix converter. I show you later, and this is possible. Two traction motors M1 and M2 are controlled by one matrix converter. So, using 5-phase machines brings some advantages. The major advantages is the higher torque density, great efficiency, and fault tolerance. Also, the electromagnetic torque pulsation and reduction of required rating per inverter leg to comparison to the three-phase motor. Also, the noise is the better using 5-phase motors. Independent control means here that the motors are controlled from one converter, including the electronic differential needed for the hybrid electric vehicle. So, I would like to note that authors of this control is a rather new control. It's not used in the practice, I think, so far. But authors, Professor Levy, in references 10 in my paper, yes, say that drivers or users don't like use this because psychedelic problem. You know, there is differential, electronic differential, if it is sufficiently or not for traffic operation. So far it's not produce such a solution. Maybe in the future it will be. So this is the last scheme. We would like to interesting in the substitute of the four quadrant converter. It was here, yes. Now is not four quadrant converter. Just the matrix converters are possible to use some set of contactors to switch over to the charging, to the traction and recuperation and so on. So this is the scheme we would like to investigate in the future in more detail. This picture is redrawn from the PhD works of our department. Original is Fuji Electric, Japan. That means that the IGBT, standard IGBT, and is comparing with reverse blocking IGBT. So the power loss of this in these devices is smaller, as you can see. It depends on the switching frequency, of course, and depends on the loading. That is interesting. So now we would like to talk about modeling and simulation. So this is the first scheme with 4 quadrant converter and 3x5 matrix converter and induction motor. And this is without 4 quadrant converter, direct to the matrix converter as 0x5. That means DC input and 5-phase output for the traction motor, induction motor. Okay. So this is the result. I will not talk about directly about the simulation because it's known, I think, this method today, nowadays. So this is the result for direct accu batteries to the traction motor using matrix converter, and this is using 4 quadrant converters. So the result is nearly the same, but the power losses in the 4 quadrant converters, this is here and this is not here. It is direct from battery through the matrix converter to the motor. This one. About simulation, we have used the indirect control of matrix converter. That means this is the fictitious DC link, VDC, that means fictitious DC link. For simulation it's possible to use such a scheme, but we have used another one, classical, as is in this figure. So the simulation was done with matrix MATLAB Simulink, but it's necessary to note that that we have used lookup tables, which are comprises the nonlinear function of the dependency of the switching energies and power losses on collector current of IGBT and the junction of temperature of the junction of the IGBT. So using similar manner is using also for diode losses. It were calculated also diode inside in the IGBTs. And Forrester model was used for the thermal calculation. It's rather new. The used IGBT transistor type for three-phase matrix converter is what was used. These devices, you can see the voltage and current, and this is the diode current, the yellow denotes, and this is for far phase. This is the smaller current and smaller current for the diodes. So as a result of the simulation is this is three-phase current is classical, and this is five-phase. You can see this the switching losses of IGBT, conduction losses of IGBT, and conduction losses of diode, and on the right side is the junction temperature about 65 grados of Celsius. This is for three-phase. This written here 3x3 matrix converter. For the 3x5 matrix converter, the result is very similar, and this comparison is in the next table. So this is the start is rather different, but it doesn't matter because this is the steady state. We have calculated the steady state, the efficiency, of course, not during start. Okay. So this is the result in two tables. This is three-phase matrix converter, and this is five-phase matrix converter. As you can see, the result is nearly the same. It's the not mainly different between result of this. That means that a five-phase matrix converter under the same of the voltage, under the same of the power is the efficiency is nearly the same. Is written here, of course. Actually, is the five-phase matrix converter slightly better by 0.15%. Average temperature is in both cases is 65 degrees of Celsius, and using five-phase machines supplied by one matrix converter, and dilation of 4 quadrant. Converter brings better efficiency. Similarly, using of the reverse blocking IGBT increase the efficiency. This is we can conclude that based on comparison of the three-phase voltage inverter with rectifier and three-phase matrix converter was done already in reference 7 in my paper, and carried out results from table 2 of my paper. We can conclude that efficiency 3x5 matrix converter is certainly better than three-phase with rectifier. VSI, that means voltage inverter with rectifier. So this is the way how to is possible to improve the efficiency of hybrid electric vehicle. Detailed calculation for VSI inverters was done before this. I will refer it. I will talk about this in another paper of this conference tomorrow. Okay, it's all, I think.
Okay, thank you for your presentation. Asking for a question, yes, please.
This method that you have applied, what is the method you have applied for the switching loss minimization? That switching loss minimization, switching loss is showing that 127 watt per switch. It is showing from your result. So what method you have applied that for this switching loss minimization?
Switching loss minimization is I would like to use another IGBT. I have shown this figure here. So it's depend on the switching clauses. So if you use the small switching clauses, the different is the higher during if we use the smaller switching clauses as different in this with higher switching frequency here. It's all today what I say. We will investigate it in the frame of the project we have in the next work.
Because the maximum impact over this high frequency switching, the switching loss is the main criteria, how to maintain this, how to reliably operate this.
Not only switching losses, we would like to all power losses in the devices to be smaller.
And it is a hard switching.
Yes. No, high.
Hard switching technique.
High. You know, this is application interaction. There is not possible to very high switching frequency. Yes. It depends on the power, and if power is higher, so switching frequency cannot be very high. Should be smaller.
Yes, please.
Which control methods did you use for matrix converter? Space vector modulation or Venturi modulation?
There is not here. There is not here in this paper. We have with the space vector control. Space vector control. Okay.
Any more questions? Okay, then just some question. You told me that Professor Levy never realized this type of converters. He didn't make a prototype. He just make simulation results.
Prototype, yes, prototype, but not in the praxis.
Yes, they didn't use in the practice. Yes,
not produced, but by the.
Yes, is your plan also to make prototype on your faculty?
We are working on this.
Okay.
But in the power measure will be not high, maybe 7.5 kilowatts only, because it's problem with the big.
Okay. And this you use this only for induction machine, so in simulation results.
We are interested in induction machine, but I think it's no problem. Mary has the paper with the synchronous machine also.
It's PM.
PM synchronous.
Okay. Thank you. Thank you for now. Our next presenter is coming from India. Hello. This is Professor Pradip Kumar Sadhu. He will talk about the lifespan of power cable. Will you open your presentation, please? Okay, please.
So we have the little bit time over this discussion. The title is Fast Estimating Method of Effective Life of Power Cable in Industrial Environment. Basically, the affiliation from Indian School of Mines, ISM, was established by British government, Royal British government, pre-independence of India. And it is an institute which was established in 1926. Now under India government directly, it is working under Center of Excellence and Center of Eminence. It is the Indian Institute of Technology, ISM Dhanbad. So there the Shivprakash Bihari and there's Anik Goswami. Both are Utpal Goswami, all are research scholars. Under my guidance they are working. Utpal Goswami already received the PhD degree. And now Shivprakash Bihari is working under my guidance, and myself, the professors P.K. Sadhu, Kumar Sadhu, currently professor and ex-head of the department of Electrical Engineering Department, Indian Institute of Technology, ISM Dhanbad. So my topic is fast estimating method of effective life of power cable in industrial environment. It is basically for critical industries. The ISM, Indian School of Mines, is the pioneer in India, in Asian countries. The Indian School of Mines is basically the mining engineering department is very much important there, and we are looking after the Department of Electrical Engineering. We are looking after the safety of these mines, electrical safety. Then under the regulation of Government of India, DGMS, Director General of Mine Safety. These are the concerns we are serving there, that for this electrical safety, and lacuna in this topic, that whenever we are discussing for the general cable failure for the industries, it is not a matter of factor. If you have in the store, all the cables are there, you replace this cable, not a problem. But for the acute mining industries, where that underground mines and the open cast mines, there India has a lot of opportunity of this mining sector. In petroleum sector, also this cable has a vital role. And what is the vital role? That whenever this cable part is the most vulnerable part of the electrical power system there. That in the underground mines, that whenever it is a gaseous and inflammable mines, so there, if cable failure is there and little bit of rise of temperature in the cable and that cable insulation failure is there, mine fires. That you have seen that lot of mine fires in China, in India, that so many accidents has been occurred and loss of life. These are the domain of this research. And from this cable, manufacturer all over the world, they are specifying the life period or whatever the life. It is a 20 years life or 10 years or 15 years life over this fundamental frequency 60 Hertz or 50 Hertz. That depends on that, the lives are coming. But due to using of today's power electronics converter, nonlinear loads, they are coming, and due to that the injection of harmonics in the lines there, we have surveyed this so many accidents in India, as well as in Hong Kong. Also, we have presented some this thing that from the before failure of this cable, you can estimate this, and it is experimentally as well as it can be possible that mathematical analysis, the rigorous analysis. So my topics are objective, network diagram, determination of final temperature rise of single and 3-core XLP cable, experimental validation, conclusion, and before starting these chapters, already we have discussed this mining industries, the most vulnerable part in power system is the cable. Everywhere it is FLP enclosures are there, that flame-proof enclosures. That means if some fires will occur, that will extinguish this fire automatically. But this cable part is the most vulnerable part from where the mines catch fire. So here the experimental validation, conclusions are there. So objective due to increasing of application of nonlinear loads and power quality of the supply is severely disturbed, and these harmonics results in increasing the cable resistance, basically the conductor resistance. The fixity, or in case of the your virtual domain, whenever the harmonics are there with the 50 Hz, that 250 Hz frequency, 350 Hz, and in the level of kilohertz, so these frequencies will create the trouble with the generating of the more resistance over this conductor. What is the more resistance? It is basically the skin effect in power system over a transmission line, that we have known that whenever frequencies are more, so skin effect is there, and skin effect will give you this the more resistance, and more resistance in the conductor cables. So at that time, this I square hard heating, that means basically heat generated in the conductors will be more for this third component, for the fifth harmonics component, for the seventh harmonics component. These things are coming, and as well as this another important part, that whenever it will give this, another stress will be decreased of dielectric strength of the insulations, that XLP. How it is that whenever injected the harmonics, that frequency is high, and XC will be directly that inversely proportional 1 by 2 pi FC, that this C will create the another drastical effect in the insulation of the cable. So amalgamation attack over this cable, it will degrade the lifespan of this cable, and it is very, very dangerous that due to this action, some in hydroelectric power stations, in overhead power systems, also the generating system cable, that failure of this cable at the time of switching. So this thing is there. We have studied for the critical industries, for mines industries. In overhead systems also there. So increment of RMS current, cable resistance is results in the increment of joule loss of the cable. So this paper describes a method of determining cable temperature rise with respect to harmonic current present. So these are the mines, the diagram, underground, and major part is basically in underground mines that cables are connected over these connections, and these cables are vulnerable part over these inflammable mines. So data considered in cable model, these data are available from the world manufacturer of this cable, and there we have collected this thickness, this design cable data, and this presence of harmonic current in supply system, that here you see that for first order this is the 100% current, for third harmonic portion this is a 50% harmonic current. So this is the distribution of, and up to ninth harmonics, here you see that up to ninth harmonics the role of the maximum losses generation is there. So these are the studied, and here this determination of final temperature rise of single core cable, here it is presented for 3 core cable, 3.5 core cable already we have studied in the laboratory, and there the experimental validation already done. Show this, here this determination of final temperature rise of single core cable is same. Different formulas are available for this empirical analysis for this 3.5 core, single core, 3 core cables. So in this case, basically the final temperature rise, this is the main thing, final temperature rise due to harmonic frequency in degree centigrade, and that will affect the life of the cable. So this is the experimental validation system. So experimental validation system, here you see that this is your requirement of wanted high frequency signal. That means that in the power frequency in the lab, if it is not available, intentionally we have injected this different order of harmonics in this power cable. Show how it is possible that here this from the signal generator we have generated that with the in India basically fundamental frequency is 50 hertz, and for single phase it is 230 volt, in LT line 415 volt, in mines, underground mines, that 3.3 kV and 6.6 kV supply is there allowed for this power system, and on the whole phase it is only 550 volt AC. That is a separate different voltages are applied according to the DGMS rule there. Show this cable here, after generating this signal, this power amplifier, from this power amplifier it is basically a power electronics converter. Intentional injection is there over this line, and this current transformer will create enhance this number, that maximum current magnitude, which is remarked by the manufacturer, maximum limit. So there it has been connected over this connection, and there are 2 data loggers are there. The one data logger will take this temperature signal. For this thermocouple, it will take this A is the ambient temperature, it will compare, and B and C, that is therefore the different requirements, the distance of this thermocouple B and C will be injected, that it will be fixed over this cable insulation, and what is the temperature will collect. And this ammeter, this is the injection of power amplifier, this current, but this side there is the maximum voltage generation for this. So this side whatever the current is there, it will be multiplying factor with this we can calculate. Next is for your registering method of this, what are the injection of harmonics are there. So there's a spectra quest is there, sorry. So this is basically a data acquisition system. There we will collect this data that in this period of time we have injected this type of this fundamental frequency with that hard order harmonics, we have injected this 5th order, or the amalgamation of this 3rd, 5th, 7th, 8th, whatever your harmonics is there, so we will inject, and with this we can continuously data can be stored. So these are the experimental method in the lab. So here the cable is this one, and basically we have tested. So temperature rise, this peak temperature rise at what frequency it has been detected. So these are the technical specification of harmonic simulator for signal generator. It is available in the net also. So it is this arrangement, this equation, that equipment type. So this is a maximum current generating capacity is 700 ampere. So largest side, and tested over this 1 foot by 1 feet, that whatever the distance has been covered. This is the
specification of simulator, then class, then temperature instability, the characteristics of the pulses, what are the types of pulses are injected, so time interval between the data points. So these are all the setup. The current transformer is used, the 1000:1. So these are the basically specification. And this temperature rise is that thermocouple A detected the 50 degree centigrade, thermocouple B is 90 degree centigrade, thermocouple C, it is basically the 92 degree centigrade. You know that the India is a tropical country. There the ambient temperature is so high that in Delhi 2 days before, whenever I collecting my diesel, so in Delhi temperature is 46 degree centigrade on that day. So and Dhanbad is supercritical zone. So there the mines, and Dhanbad is the coal capital of India. It is declared in India government. So here the temperature, this thermocouple A, basically the ambient temperature census. So ambient temperature on that day, it is a 50 degree centigrade. And this is one of the failure result, that one of the failure cause in India or tropical countries, that ambient temperature also so high. So these are the results. So results are already taken. So if you are interested, we can discuss over this. The life estimation of this power cable, these references are given in full length paper. If you are interested, that their references are given. So from this reference you can put this, and whatever the life decrement, it will be given by this formula. So these are the presence of harmonic frequency is responsible for the temperature rise of any power system network, and the temperature of thermosensor C, which is strategically located at touching position of cable to identify both skin and proximity effect, gives higher temperature rise in cable compared to temperature rise of non-touching position of cable measured by sensors B. So temperature here, it is also quite evident that if in a power system network where significant amount of harmonic frequency is present in power system network, LT cables should not be laying in touch formation. So these are the another precaution, and without this, that you can ask this question, that the injection of harmonics, it is basically coming from the power electronics converter. That's why that without power electronics converter, we cannot run this industry, as because the energy efficiency and energy efficient converter, but at the same time, we have to see this reliability of your equipment health. So this conclusions from the life estimation calculation of power cable, it is very clear in presence of higher order harmonic frequency and cable operating temperature increment by around 3 degrees centigrade, the effective life of power cable is reduced by 2928 days. It is almost the 5 years or 6 years. It will be drastically reduced for this. And these are the conditions, these are the estimation. If you first estimate, you can replace this cable whenever it is healthy. It is looking like healthy, but it is punctured inside this. Already it has been ruined, the cable health. So that's why that first estimation method is much more. For this method is required for the supercritical industries applications. And in the petroleum sector also same thing. We have the Bombay High, the ONGC platforms are there for the extracting the petroleum crude, as well as this. There also the super inflammable areas. So there we have to take care about this, the life health or health of the cable, as because at the time of starting we have said this cable is the most vulnerable part of the power system of supercritical industries. As because the cable has no FLP enclosure, that's why. Thank you.
Thank you. Questions? Perhaps one, you talk about 3,000 days of
Yes.
the decreasing of effective lifespan. Yes. What is the nominal lifespan of this cable?
Normal lifespan of the cable
Yes.
is power cable is basically for the 20 years to 15 years, 15 to 20 years, 25 years. Some depends on the voltage gradient.
Okay.
That if the high tension cables are there using in the mines, that even 6.6 kV cables are used. So there the your lifespan is more or less 18 to 20 years. And out of 20 years, if the
This is
4
10
5
years,
years
yes,
it is,
yes, yes.
that means that it will be deducted from this lifespan. So it will be directly affect your economy and your investment.
Yes, yes. Did somebody already use?
As well as you cannot avoid this thing that at the time of healthy condition, you can get the idea about this in your mind. It has been fixed to 20 to 25 years after you will replace the cable. But the thing is, accident will be happened that maybe it will be happened before that 10 years or after 10 years. That and so many accident has been occurred in China. Basically, we have studied this China accident in India, that 90% mine fire hazard has been done, or in the crude industry, petroleum crude industry also, the same thing, it has been happened due to the failure of cables, as because this is the most vulnerable part. There are no FLP enclosure. For transformer, FLP enclosures are there. For your fluorescent light, the everything in LED, all the solid state lighting, you have the fluorescent, that FLP enclosure. That means flame proof enclosure. So it cannot catch fire. It will prevent this thing. That elongate this fire flame in the path, so it will be reduce the temperature and it will not catch fire. But the cable is the vulnerable part. There is no casing of the flame proof enclosure. So that's why there maybe catch fire. And there are so many applications are there in underground mines, like the machines of shovel, then your drag line, then another is the drum cutter system. That wall of coal will be cutting the tons of coal within this the time of 1 hour time. That you can remove this, and this all the induction motors have no starter. So whenever I have joined Indian School of Mines, after studying this so many things, that I am searching a new path, that there in the drag line and shovel, that this type of technology is there. It is starting on 100 ampere current, 300 ampere current over this dual starter due to the starting torque.
Okay, thank you once again. No question anymore. Thank you. Our third presenter is coming from Turkey. This is Associated Professor Bahadir Akbal. Please come. Yes. The title of the paper is MSSB to prevent cable termination faults for long high voltage underground cable lines. Please.
Welcome to my presentation. My name is Bahadir Akbal from Turkey, Konya Technical University. My paper is related to high voltage underground cable lines and grounding. My presentation is MSSB to prevent cable termination faults for long high voltage underground cable lines. Transmission of electrical energy, high voltage transmission is made by using two ways. These ways, overhead lines and underground cable lines. Overhead lines, transmission tower, insulator and conductor are the most important materials for high voltage overhead lines. Tower structure and number of insulators varies according to line high voltage level. If voltage level increases, size of tower and number of insulators increase. To provide electrical insulation, and towers are shown in figure 1 and overhead lines are shown in figure 2, and transmission line insulation are shown figure 3. Different structure types of according to high voltage level, overhead lines and transmission line insulation. This insulation is a pin type insulation. Overhead lines are used for transmission of electrical energy. However, these lines cause some safety problems in city center or crowded areas. These problems can be tower collapse, electroshock, and arc flash and fire. Some problems are shown in figure 4 and figure 5. Hence, high voltage underground cable lines are used in these regions. Figure 4 and figure 5, collapsed tower. Also, in figure 6 and figure 7, risk zones of transmission line and fire risk of transmission line. High voltage underground cable lines. High voltage underground cable has an insulation layer to prevent short circuit, and high voltage underground cable occurs from different layers. These layers are shown in figure 8. Also, underground cable line is used for installation of high voltage underground cable line. This channel protects high voltage cable against the heavy working condition and environmental effects. This channel show in figure 9. High voltage cable and these lines, and standard cable channel for a single core cable, and cable channel for 3-phase system. Metallic sheet is used to protect insulation layer of high voltage cables against the environmental effects. However, the sheet current occurs on metallic sheet of high voltage underground cable line, and sheet current can be called as circulating current. This case is shown in figure 11. Circulating current, head of line and end of line. Sheet current generates sheet voltage on metallic sheet of high voltage cable. If sheet voltage is bigger than touch voltage limit value, electroshock risk occurs for human. Also, sheet voltage causes cable faults. Cable faults generally occurs as insulation faults and cable termination faults. These faults are shown in figures. Insulation faults and cable termination faults. Metallic sheet of cable must be grounded to prevent sheet current effects. Different type bonding methods are used to ground metallic sheets. These methods in literature: single point bonding, solid bonding, cross bonding, and sectional solid bonding. Single point bonding is shown in this figure. If a single point bonding will be used, high voltage line length should be less than 200 meters. Otherwise, high voltage occurs end of high voltage cable line. Thus, solid bonding and cross bonding methods are used for long high voltage underground cable lines. Solid bonding, cross bonding are shown in figures. Solid bonding and cross bonding. However, sheet voltage SV of cross bonding method is generally more than solid bonding method and touch voltage limits. So solid bonding can be suggested for bonding of cable. However, SV of solid bonding can exceed touch voltage limits in case of increase of unbalanced fast current and harmonic distortion. When SSB is used, SV does not exceed touch voltage limit for human. SSB shown in this figure. However, if length of cable line exceeds 1 kilometer, harmonic distortion rate and SV increase due to cable capacitance. So cable termination fault occurs in cable line. Thus the modified SSB, MSSB, is developed for long high voltage underground cable line under high voltage distortion case. In this paper, MSSB method is shown in figure 18. This is method for cable bonding, modified sectional bonding, MSSB. In MSSB, total line length is called as major part, and major part consists of minor parts. Minor part parameters are minor part length, distance of between phases, grounding resistance, grounding inductance, These parameters should be optimized to obtain most economical and technical results. However, SV should be known to make optimization of MSSB. Thus, SV of high voltage underground cable line is forecasted by using different artificial neural network (ANN) and hybrid artificial neural network (HANN). After SV determined, minor part parameters are optimized by using optimization methods according to touch voltage limits value, genetic algorithm, particle swarm optimization, and differential evolution algorithm are used for optimization MSSB. In this study, high voltage underground cable is modeled in PSCADE simulation program, and simulation of high voltage underground cable lines are made to determine SV, sheet voltage. In PSCADE, different high voltage underground cable lines are modeled, and SV of these lines are measured. It is seen at the end of simulation studies that many factors affect sheet voltage. These factors: three-phase currents, neutral currents, harmonic currents, total harmonic distortion rate current, end of line, total harmonic distortion rate of voltage, end of line, cable line length, distance between phases, and grounding resistance. These factors are used to forecast SV in ANN and HANN. In HANN, weights of ANN are updated by using optimization method. These methods, similarly, differential evolution algorithm, particle swarm optimization, and genetic algorithm. Training and forecasting errors of different ANN networks and HANN methods are compared, and these results are shown in table 1. These methods, training errors and forecasting errors. Different ANN type, there's hybrid ANN methods, HANN. It is seen in table 1 that training and forecasting errors of HANN methods are generally lower than the other errors of ANN networks type. After is SV is determined, optimization of MSSB can be made. In simulation studies, SSB and MSSB are optimized, and results of SSB, MSSB, and solid bonding are compared for long high voltage underground cable lines. Also, high harmonic distortion is considered during simulation studies. Genetic algorithm, particle swarm optimization, and differential evolution algorithm are used for optimization of SSB and MSSB. In simulation studies, total harmonic voltage distortion of electrical network is accepted 5%, and touch voltage limit is accepted 71 voltage peak. The result of solid bonding is shown in figure 1. In this bonding, SV is bigger than touch voltage, and harmonic distortion is bigger than limits. When a genetic algorithm is used for optimization of SSB and MSSB, these results SSB and MSSB. It is seen that SV for SSB and this is MSSB for SV voltage. Also, harmonic distortion is bigger than limits. Harmonic distortion is lower than limits. When particle swarm optimization is used for optimization of SSB and MSSB, these results is for SSB, SV value and total harmonic distortion value is bigger than limits. Also, MSSB results SV and harmonic distortion values are lower than limits. When differential evolution algorithm is used for optimization of SSB and MSSB, these results for SSB, these results for MSSB. Similarly, SV is bigger than touch voltage, and harmonic distortion is bigger than limits. But MSSB, in MSSB, SV is lower than limit touch voltage, and harmonic distortion is lower than limit. Conclusion. In this study, MSSB method is developed to prevent cable termination faults for long, high voltage underground cable lines under high harmonic distortion rate. Different ANN network types and HANN networks are used to forecast SV of long high voltage. Forecasting errors of HANN methods are lower than ANN methods. After SV is forecasted by HANN methods, MSSB parameters are determined. When SP and SSB methods are used for long high voltage underground cable lines, harmonic distortion rates of these methods exceed harmonic distortion limit, and SV of these methods exceed touch voltage limit. When SSB method is used for bonding of long high voltage underground cable line, harmonic distortion rate of MSSB does not exceed harmonic distortion limit, and SV of MSSB does not exceed touch voltage limit at cable termination. Namely, MSSB is suitable for bonding of long high voltage underground cable line that will be connected the electric network with high harmonic distortion rate. Thank you very much.
Thank you to you. So, should we start with the questions? Please.
Can you explain such thing? Three phases, they are put in individual shields. Why not three phases put into one shield? Because then you will get rid significantly of this sheet current. So what is the reason that each cable is separate?
Sheet current occurs generally occurs
No, I'm not asking how it occurs. I understand that you have transformer, and this is it. If you have a current flowing in the cable, so you have a current. But if you put three phases together, then the magnetic fields made by those three phases, they will cancel. You will not have the sheet current. What is the reason that they put three cables separately, not cables together, and then the sheet?
Yes. High voltage cable is very big, and high voltage cable has an insulation layer. Therefore, installation of high voltage cable is very difficult, and if weather is very cold, high voltage cable is very difficult installation. So a single core cable is very used.
But the losses, everything, I'm not able to find an excuse. The breakdown voltage that you are saying, you still have the same voltage from the phase to the sheet. And if you put two cables together, so the insulation thickness is doubled. So it's not the low voltage. The only explanation is what you are saying is readiness of the cable. But nobody cares. I'm just confused. Thank you.
Yes, please.
To question that, I have little bit confused with the first part, that you have shown the tower failure, how it is linked with your present topic. That in the first slide, I have seen your high voltage tower failure. This is the open transmission line. Yes. How it is correlated with your topic, that these failures are not related with the cable failure?
Cable failure generally harmonics increases insulation layer temperature.
My question is it required the overhead transmission line presentations with your topic presentations? Is it correlated? That's why I have asked this one thing. Another, you go to your equivalent circuit only. Cable part. Yes.
This?
No. You go to it. Go. Next. Yes. In this circuit here, you have shown this minor part. It is a equivalent diagram. You have shown this LG.
LG?
Yes.
LG is used to prevent parallel resonance.
Pardon, please?
LG is used to prevent parallel resonance.
Parallel resonance.
Yes, parallel resonance. Cable capacitance and inductance of load occurs parallel resonance, and voltage is very increases. LG is used for parallel resonance to prevent.
Any more questions? Okay, the presentation was very interesting because the overhead underground cables are very topical now. Now you know that in Germany they try to connect North Germany with South with underground cable. But what is the price compared to overhead
I
lines?
not compare it. Price.
They are 10 times more expensive, or? Okay, but your suggested modified solid section,
Evet. Sectional solid bonding.
Yes, is even more expensive than
No.
There is only the
LG is passive elements.
Okay.
Only inductance.
okay. Then it's the same. Thank you very much once again. At the beginning of the section, one of the presenter was missing. Is perhaps he already here? His name is Yujun Leo. No. Then we have only one presentation. The title of the paper is Rotary Wireless Inductive Transmitter Powered by ZV8 Resonant Converter, and the presenter is Professor Gargana Vicheva. Please.
Good afternoon, Mr. Chairman, dear colleagues. My name is Gergana Vacheva and I am PhD student in Technical University of Sofia, Department of Power Electronics. Today I will present you our paper, which is entitled Rotary Wireless Inductive Transmitter Powered by Zero Voltage Switch Resonant Converter. Me and my colleagues are made this paper, and today I will present it. So briefly I will present you the content of this presentation. I will show you some introduction, the main idea, what exactly is the rotary wireless power transmitter. After that I will present you simulation and experimental results, and I will say some words as a conclusion. As introduction, I can say that the recent years wireless power has already become common in our everyday life and has a potential for numerous applications in the manufacturing and transportation sectors. The development of this field of power electronics is also a result of the advance in manufacturing of power electronics switches and passive elements. The optimized operation of these power electronics converters and newly developed ferromagnetic materials with improved characteristics lead to a reduction of the losses, improved magnetic coupling, and efficiency of this conversion. The manufacturing of magnetodielectric materials allows for a variety of magnetic core and concentrator designs. All of these mentioned purposes open new horizon for development of wireless power transmitter that can replace ordinary mechanical contact systems for supplying power to rotating parts, which could result in increased reliability and reduced maintenance of the different type of manufacturing equipment. So here in this diagram is presented a cross section of rotating platform, which is that part of this, which illustrates the structure and principle of operation, the driving motors and pneumatic part of the synchronization sensors, and also a rotary wireless transformer, and is shown this graphic. So here we have pneumatic mechanism which is connected with this line to wireless communication. And so here is the primary controller, the secondary controller, and after that we have the transmitter core, which is here, and also the transmitter core, and respectively to that here is the receiver core and receiver coil. So this is the primary control signals, and the idea is to when we make some rotation of the different parts to transmit energy with wireless communication. So this is the scheme that is used as power circuits. That is two type of converters. That is we used zero voltage switching resonant converter. So that is this time here we have some current transformer, which is the primary winding and the secondary winding, which is supplying the rectifier, and the specific one of this type of structure is that we have some CLC filter which is connected between the rectifier and the volt. And the idea of that is to change the possibility to change the value of the volt. So here is presented the design of rotary wireless power transmitter and electromagnetic processes. Also, there's two basic structure of this type. One of them is axial and the other one is radial. So here in this diagram is presented the electromagnetic circuits of radial rotary wireless transformer used in construction of the rotary parts. And in this figure is depicted the main geometric parameters. So here we have the width and the length, which is here, the length of the windings of the transmitter coil and the receiving coil. Also we have the internal radius and the other values of the transmitter coil and the transmitter core. The idea we have also the delta, which is the air gap between the receiver and the transmitter coil. By optimization of these values of the length of and width and the other geometric dimension, an improvement of magnetic coupling between both coils and reduction of parasitic parameters can be achieved. Here also with R is denoted the magnetic reluctance of the rotary wireless transmitter. They form a magnetic circuits with lengths, which is presented here, and as the intensity of the field through them is constant. So with this equation is presented the sum of the individual lengths which is given with the average length of the magnetic core. So here is the sum of all lengths for the different values, different parameters. So here is presented the equivalent circuit of a rotary wireless transmitter. So basically we have some generator. Here in series is connected the current transformer. After that we have the rectifier, the DC-DC converter, and after that we have the volt. Here is presented the electromagnetic energy stored in a defined volume, which is comprising to the rotary wireless transmitter core, air gap, and primary winding leakage, which is denoted with L1, and the magnetizing inductance, which is denoted with LM1. This electromagnetic energy could be described with this equation, and the field in the transmitting and receiving coils for the distance Hx is between these two radius, radius R2, which is minor to Hx, and which is minor to R3. And the field strength in the air gap are defined by the following expression, which is equation 3. And when we use these two equations, we can obtain the average value of the field strength of the transmitting coil, which become this equation. Here we have some diagram of the magnetic flux in this type of rotary wireless transmitter. Here is presented the currents flowing to the transmitter and receiver coils that generate magnetic flux, which is denoted by Phi1 and Phi2. And the main flux is generated by the current flowing to the both coils, and could be described with this equation, which is the sum of the two flux, which is passing to the magnetic core, and the flux generated by the leakage inductance is presented with this equation, and that is the result of the flux in the rotary wireless transmitter. Here is presented some simulation results of the designed radio rotary wireless transmitter. The analysis of these results shows that the designed core also shields the field and satisfies the electromagnetic compatibility criteria due to the flux density outside its magnetic core. It's less than 15 microtesla. The inequality distributed flux density is stronger in the direction parallel to the rotational axis, that is between the two in this order. According to the existing standards for electromagnetic fields dissipation, the approved safety level for frequency up to 150 kHz are flux which is equal to 27 microtesla. So here is presented some table which describe the experimental results with active load in the receiver coil. Here we have the two equations for the power and the efficiency. So here we have the voltage, the current, and the power factor, and the two active power of the transmitter and receiver coil. The idea here is that we change the value of the air gap from 2 to 20 millimeters, and also we change the coupling ratio from 0.2 to 0.8. And the more significant part of this is that we obtain high efficiency. Here we can see this is the voltage, the current of the primary coil, the power, and also is presented the voltage and the current of the secondary coil. And here you can see that with the increasing of the coupling ratio between this value 0.6 and 0.8, we increase our efficiency of this type of resonant converter. And when we decrease this ratio, also the effectiveness decrease significantly. Here is presented, in order to study this zero voltage switch converter operation computer, simulation and experimental tests are implemented. Here is presented the value of all the elements. So we have the input voltage, the value of the inductance of the resonant converter. Also, this is the value of the capacitor in the resonant converter. This is the primary inductance, and also here in the secondary inductance is presented the value of the filter. Also, we have the load, the value of the load, and the working operating frequency, which is the 38.5 kilohertz. And we use in this case the coupling ratio, which is equal to 0.8. In this figure is presented the real experimental study, which is used for making these experimentals. Here is present the simulation results and for the power electronic converter, and we have in the first diagram we have the voltage across the transistor and also the current which is flowing to the inductance of the resonant converter. Here you can see that we obtain almost 160 volt, and here we also obtain the zero voltage switch. Here after that we have in these two pictures the real experimental results, which we can compare it with the simulation results. This is obtained from the oscilloscope, and here in green one we have the voltage across the transistor, and with the blue line in this curve we have the current through the inductors. Also in the second case we have simulation results of the voltage of the primary coil and the secondary coil, which is presented with the red and respectively with the blue line. And also here we have with yellow the output voltage and the two current which flow to the through the two diodes. And so as a comparison we can say that these results is found that there is very good concurrence. That means that is less than 5% difference in the simulation and experimental results. From the analysis of these results can be observed that the transistor T1 peak voltage is around 160 volts, while the voltage of the primary ripple is about 16 volts and the secondary is 6 volts. This is due to the fact that the output transformer is behaving like a current transformer, and that is the parameter have a weak influence of the resonant circuit. So here you can see the experimental waveforms of the voltage across the primary, which is on top, and the secondary winding, which is on bottom. In these two pictures, we are presented the waveform of the rectifier output current before this COC filter, which is measured with the help of shunt resistor with the value 0.1 ohm, which is connected between the rectifier and this filter. So here we can see the output voltage and the current. And in this picture we made some experimentation which is significant. We don't change the working frequency. We change the range of the load with 50% to 150% of the nominal value of this type. So here you can see how exactly is changing the load current with 50%, 100% and 150%. And as output results, you can see that the current through the resonant converter in the three cases is almost the same, and also the voltage across this transistor is almost the same. So we can say as a conclusion that with the changing of the load there's no significant difference between these results. And as a conclusion I can say that a converter with contactless power transmission and zero voltage switch is proposed with presented basic ratio for the magnetic circuit. A rotary transformer has been designed. So to ensure zero voltage switch operation, the implementation and appropriate tuning of the control system is necessary. The simulation and experimentational results confirm proper operation of the power electronic converter. Zero voltage switch operation is maintained over a range of variation of the load and magnetic coupling of the transformer. The obtained results demonstrate that the studied system is suitable for different purposes that could be platform rotating with high speed and charging energy elements such as supercapacitor or batteries, or other application in which significant variation in the load occur. The presented design methodology, analysis and prototype of construction, and experimental study are solid base for future design optimization of this type of rotary wireless transmitter with numerous possible applications for inductive wireless power. And on the other hand, the implemented zero voltage DC converter with improved characteristic ensures stable and reliable operation of the system in a broad range of parameter fluctuation. So thank you for your attention.
Thank you to you. We have some minutes for some questions, please. Yes.
Can you go to slide number 3?
Slide 3. this one.
What is ceiling inductor? The upper right corner of the drawing.
This could be induction heating or something which could be connected wireless. So when we use...
Does it has to do anything with what you present?
What?
Is it related to what you are presenting?
No, the basic
okay,
idea
so
is for the resonant converter.
Can you go to slide number 8, I guess, where you have equivalent circuit. Yes, this is it.
Yes.
Are you sure everything is correct with your leakage inductance of the transformer?
So the idea here is that we present
the
what?
equivalent circuit of the transformer. Are you sure you have drawn it correctly? Because you are connecting parallel leakage inductance to magnetizing inductance. Are you sure it should be done this way? Because later on you sum those two.
So the basic idea...
Parallel connection of two inductors is the summation?
Parallel, excuse me?
You have connected them parallelly here.
Yes.
Are you sure it is correct?
Here is presented in this way. The idea is that we make researches for the resonant converter.
Yes, but it is not the correct drawing. Okay, thank you.
Thank you.
Okay, perhaps one question about the efficiency. If you show the efficiency is very high, so for small air gap is 90% or something similar.
Yes,
did you have in mind also the mechanical losses, or these are only the efficiency between the electric power?
In this research, we don't make estimation.
Okay, in this case, also the efficiency is influenced by the speed of the rotation.
Yes, yes.
Okay. Thank you.
Thank you.
One question, short question, please.
Only one question.
Yes.
Sure.
In what is the magnitude you have tested for the wireless power transmit?
Which magnitude?
The power is not given. Empirical formulas are given, but in the test result, you have tested for how much power? It is in voltage or milliwatt or in kilowatt?
The idea here is for make it for 500 watts, but it could be make up to between 1 or 2 kilowatts.
1 or 2 kilowatts.
Yes.
Okay. Thank you very much. Thank you for questions and answers. So we finished our session. I have to say yes, thank you to all presenters and to the audience. Thank you.